Okay, let's get started. So plan for today is this. This is practical data science, right? So there are a couple of ideas floating around. You had an idea, and then someone else had a finance idea. So the first session of the class for today, I'm going to talk about these two ideas. I think not just this class, another class, someone also asked me a similar problem regarding finance and AI. So I'm going to talk a little bit about that. Basically, on a high level, stock market and making money in stock market, it's not a prediction game, right? It never will be a prediction game. Basically, what that means is if I give you tomorrow's Wall Street Journal, it's not guaranteed that you'll make money in stock market. So we're gonna talk about what that means. That's not my belief. It's a very well established belief in the industry. So if you're interested in using AI in finance, hopefully I can share a little bit of insight. So you don't like go down the rabbit hole and then be like, oh, I spent 5 hours on this and then it doesn't work, right? So we're gonna talk a little bit about that. Talk about football, so sports. So you had an idea, so we're gonna talk about that. So that's the first session. Second session, we're gonna jump back into giving you guys all the tools. And then last time we talked about a Gradio app, we talked about chatbot, right? You load the model and this is how we generate next token. So today we're gonna dive one step further, which is VLM, so vision language model. So the most easy one is image caption. So you're sending an image, you ask a question, and then it will say something back to you. So we're gonna see how that works. So hopefully you guys can, like when you guys get into building apps, like at least you get a flavor of, okay, if I wanna put image here, this is how it works. If I wanna put sentence here, this is how it works. So that's the plan for today. So first things first is finance. So let me start with this. Let me start with this one. Okay, let me zoom in a little bit. Has anyone heard of a recurrent neural network? Just raise your hand if you heard of it. So you heard of it, you heard of it. Anyone else? Okay, so a few. I'm gonna quickly walk through this. So recurrent neural network, yes. Let me check recording. That's a good question. Yes, I am. Yeah. Um, recurrent neural network. The Sorry, is that a question? Okay, okay. So recurrent neural network. Why do we do this? The point of recurrent neural network, I'm gonna explain in words and then I'll show you why we're doing this. So the point of a recurrent neural network is when your data set has timestamp, the conventional neural network does not work. Okay, I'll repeat that again. When the data set has timestamp, the conventional neural network does not work, right? So what do I mean by that? What I mean by that is any data set that has the timestamp tracking or using a timestamp as a tracking index of the sample, not just a sample as like a person take an exam grade or like a cat or like dog, not just that, right? Like you are tracking, like the data is collected in a way that the time makes sense and time changes the characteristic of that sample a little bit, right? We're not just talking about a student grade on average, like we're talking about student grade today or student grade tomorrow. So if you're doing that, then that timestamp change exactly the change of timestamp change the nature of that variable. So that inherently makes a data a time series data, right? For example, the easiest example is temperature, right? Temperature in the summer is of course going to be different than temperature in the winter. Why? Because it's different time. Very simple idea. So same thing here. This is how it works. There are two versions, right? There are two versions. There's one on the left, which is this one. There's one on the right. The one on the left is called folded recurrent neural network. And the reason they call it folded is because you don't have to draw all these circles. That's basically what that means. So I'm gonna do this twice. One on the left, one on the right, but they're basically the same picture. It's just drawn in a different way. So let's start from the left one. Left one is very simple. It's coming from this thing called a Markov chain. Uh, whoa. Let me put it here. Markov chain. So like whatever, like you can pick anything. Like this is a Markov chain. So Markov chain, like something like that is called Markov chain. So how is it defined? This is defined basically in terms of nodes and in terms of this thing called a transition probability. Transition probability basically means the probability from one node to the other for any node that's being defined in the Markov chain. So for example, here you have E and A, whatever that means. Like it can be like this is one node or one state. This is another node or another state. And then these arrows referring to probability to go from one circle to another. That's it. It's that simple. Now, this has nothing to do with time, not yet, right? People take that idea and then they put it in the neural network. And then if you do that, it effectively becomes something like this. Now, that being said, you can't just draw arrows whatever you want, right? Like you have to draw arrows in a certain direction. So you start with the input feature, and then this input feature can go into some sort of latent layer. And there's like a mathematical equation here that's basically like a linear regression. Um, so once you go from this circle to this circle, so you can kind of call this like, I don't know what the color is. I'm just gonna assume that's pink color. So you go from pink color to gray color. And then once you have gray color, you can do two things, right? One thing is you go to yourself. So that's one possibility. The second possibility is you go to the output. So the action of going to yourself, you can kind of think about that as linear regression. And then the action going to the output layer, you can also think about that as a linear regression. Now, I think this arrow and this arrow, it's more intuitive, but this arrow that goes to yourself, that's kind of like unintuitive, right? How do you go to yourself? Well, this is when time happens, right? So I'm not talking about yourself at the same time. I'm talking about yourself at a different time, right? So it's the same state, but the circle now, excuse me, the arrow here is pointing to that same node, the same node in the next time. So that's how you explain this folded graph. Now you can also retell the same story, but with an unfolded graph, and that's the graph on the right-hand side. So let me tell the story again, but with unfolded version. So unfolded version basically means this this arrow and this arrow, it's the same as what we had before. You start from an input, which is this pink box, go to your hidden layer, and then go out, make a prediction. Um, this red arrow now goes to right. Now, this gray box here is the same state, but the next timestamp, whatever that timestamp means. If it's a temperature, probably you can do like, I don't know, next hour or next whatever. If you go Google it, so whatever, temperature in New York City. So if you just do that, then this you can kind of think about it as maybe like half an hour or an hour, maybe there's like a dot here, something like that. So that would be something what I consider time series. Um, so that's that. Or you can look at stock price. You look at stock price. Sorry. Like this guy. This is S&P 500's ETF trust. So this is the spider index. It's the exchange traded funds for tracking the S&P 500, so tracking the entire market. And then every single dot here, like that's a number 662. That's a number 662. That's a number. Is it a different number? 61, right? These are different numbers, and then they're like the closing price of this index at that time, right? Now, within that minute, the stock price could still go up and down. But obviously, you're gonna have to pick a closing price like eventually. Like it doesn't matter what's a window, you're gonna have to pick a closing price eventually. So that's what these dots are. And then we're still talking about the same variable, whatever this index is, same variable, but when time changes, the number changes, the data changes. So this is also an example of a time series data. So um, so when these sets of circles go into the next state by using this red arrow, we're still looking at the same sets of circles, right? We're still looking at the same sets of circles, except that the values changes because it's a different time. So um, this should make somewhat intuitive sense. The only thing that's probably worth paying attention to is these weights. Like for example, when you go from here to here, there's some sort of like a weights and bias, right? Because it's a linear regression model. So those coefficients, or also known as parameters, they're actually fixed. Like you can't use like you can't use different parameters to predict tomorrow, and then you use different parameters to predict a week later. If you do that, that's a different model, right? Then and you shouldn't be doing that because then you're cherry picking models. Does that make sense? How you do it in reality, that's on you. But in terms of academic research, the weights should be the same. So that's just another caveat that it's a little bit unintuitive. Now, if you talk to anyone on Wall Street, they will probably tell you that's crazy. Why do you use the same strategy every day? That's probably crazy. In reality, people probably don't follow the same strategy every day. But if you're gonna backtest a model, you can't cherry pick model, right? You have to use the same model, same strategy, same weights, and then test out on different window of history of data that you have to prove that your strategy is not a one-time thing. Your strategy works all the time, right? So it's very unintuitive. That's just the nature of this research. Okay. This all sounds like we're building model, right? This all like everything I said makes sense in the end. If you're gonna say, oh, 5 minutes later, he's gonna say, we're building a model, we're trying to do a prediction. So that's correct intuition, but that's actually the wrong conclusion. So here's why. Let me finish this part and then I'll explain why that's the case. So everything here sounds like we're trying to make a prediction. Building model, here's your data. Obviously, you're trying to predict something, right? Let me show you a little bit about the code. So this is how you create a time series data. The idea is very simple. You need some sort of timeline, right? So this T here, there's nothing you can do. The T has to be 0, 1, 2, 3, 4, 5, 6, 7, 8. You have to track it using some sort of whole number, right? You can't just go nuts with like you can't go completely random with the data here as a timestamp. So this T has to happen. So that dictates that this data is a time series data. Okay, so that's one thing. So once you create data, this is why it's simple. You just create some sort of like a that can be just like linear model, right? 2x plus noise. That's just a linear model. And then now you have your x, you have your y, that you have your data, and then we're building a model, right? The model here is very simple. You can kind of think about it as simple RNN, something like that. And 10 just means it's one layer with 10 neurons. So all that's very simple. But in order to convince you guys that's the right model, I need to give you guys an example that doesn't work, right? So this is what I mean by that. So you create your data, that's your data, X, and then you plot it. It looks like that, right? It's a sine function, it's cyclical. It's not going all the way up, it's not going all the way down. It always stay in this middle range, right? Because sine is bounded, right? Bounded by 1 on the top and -1 on the bottom. So now you create noise. So what noise do to your data? Come on in. What noise do to your data is it no longer is a smooth line, right? Now the line is like wiggle, right? Zigzag, right? So you plot it, the original data, the sine function, and now the one with the noise, it will look like this. The blue line is the original sine function, and the orange line, the zigzag one, that's the data plus noise. So now you have this data set. Now you can think about one line as a feature and the other line as the thing that you're trying to predict, right? So the best case scenario is you can kind of use the blue line to get like another sine function that's kind of like going up a little bit. That's kind of like the best case scenario. If you are able to predict something that very closely track this orange line, chances are you probably overfit. So let's see what the result look like with two sets of models. Here you can build this model that has nothing that there's no RNN inside, right? There's nothing here says anything about RNN, right? This is just you flatten it, so it's just a vector, and then you just build a dense layer. And dense layer, it's just a conventional neural network. There's no RNN whatsoever. There's no time series. There's no sequential data. Nothing like that. You can use dense layer to build this model. You can compile and then you can fit it. Once you fit it, you're gonna see something that looks like this. So blue line, I just explained that's a feature. This orange line is a target. That's the one with the noise, right? Zigzag. This green line is a prediction without the RNN model. And you can look at the sucks, right? This is nowhere close to this one. It's nowhere close to this one. So obviously the model has no clue what is it that we're trying to predict, right? You plot the prediction, it's nowhere close to what the real data is. So this error is too large that you can safely conclude that this green line just doesn't do the job. Because that's the argument here. So what we just saw is a conventional neural network doesn't learn anything, right? It doesn't learn time series pattern. That's basically what that picture tells you. Now, let me give you the same version, but let's swap the model to RNN, right? So that's how you tell the story. You use same data, but you change different model, and then you see what the performance is. So now here, I'm using the code I mentioned above, simple RNN. Now here has RNN, and then that means the model is designed to tackle cyclical data, like time series data. So same thing, compile, same thing, dot fit. Once you do all that stuff, you can train a little bit and you plot it. Now this red line is the prediction with the RNN. So red line is with RNN, a green line we just saw is without RNN, and then a blue is a feature, and the orange line, the zigzag one, is the one with noise. And obviously now you can say, okay, the red line is very close to the orange line, but it doesn't really zigzag exactly like the orange line. It shouldn't, right? Because it's still linear regression. Like you're still trying to predict the average number. You're not predicting exactly which zigzag that you're going. If you're able to do that, then you're probably overfitting, and that's not a good thing. But for the time being, you can safely conclude that the red line does a much better job than the green line, right? The red line is here, this guy here in the middle of the zigzag. The green line is this guy here. So that should be very straightforward, right? This is the story about prediction. This is a story about RNN using neural network to make a prediction. And this is a story about using basically a neural network to predict time series data. Now, all the way to here, you're still in the AI world. You have not touched about stock market, not yet, right? So it's very intuitive that people look at this and say, okay, I got it. I'm gonna apply this on stock market. So right in the beginning, you're gonna have to rethink how do you engineer data a little bit, right? Because stock market does not look like this orange line, right? Obviously it does not, right? So you can go to this chart and just say max, and then the S&P 500 has been going up since pretty much I don't know 1993, right? 992, 993 here. It's pretty much been going up. So first of all, if you just look at the price, it's like obviously not cyclical, right? So you cannot apply, whatever's working here, you cannot directly apply on stock price. Make sense? So that's caveat number one. The second one is now people are like, doing out of box thinking, right? Okay, so I can apply on this, but what if I apply on stock returns? So that's like a fair argument, right? So what's happening there is you can go to stock return. You'll probably see some chart like this, or this is a good chart. So if you calculate the returns of stock price, not just stock price, the original price. If you just look at the return, but then now the next problem is, okay, what is your time frame? Are you looking at daily return? Are you looking at monthly return? Are you looking at quarterly return? If you look at quarterly return, you're gonna go back to the same problem again. So let me open this tab here. If you go back to if your timeline is so large to a point that everything's going up, then all the returns will all be positive. That's still a problem because if everything is positive, then you're not predicting that something cyclical because it always goes up, right? So now naturally people think, okay, I'm gonna predict, I'm gonna take the return on a daily time frame or even smaller than that, right? So what you're gonna get is something that's kind of like this. Now there's still a problem, right? Because if you take a look at the smaller time frame, sure, you can probably zero out to close to mean, but you're gonna still get this average that's like still positive. Does that make sense? And the reason is because that chart is still going up, right? So if you're predicting something like this, what you're effectively doing is you're predicting an orange line that is kind of like shifted up a little bit with like just complete randomness. There's no straight pattern. It just as time go forward, this orange line just slowly go up. So that's first of all destroys the assumption of whatever's working here still works in stock market. It doesn't mean it doesn't work. It just means the nature of stock price data already destroyed the assumption that it's supposed to that it's supposed to be working for RNN. Does that make sense? Okay, so now the question is, okay, then what works, right? I just gave you a whole lecture that doesn't work, but then you can't just say that, right? Like what works then? You have to offer an alternative. So what works is you have to rethink about this problem a little bit. So stock market, excuse me, in this world, end of the day, it's actually not a prediction game. It's actually a optimization game. So it's not about how well you can predict the future price. It's more about what can you do today so that overall you're optimized. Like your risk doesn't go to a point that you're uncomfortable with, or that your reward doesn't cover. So end of the day, become a problem like that. And that's actually not a prediction game problem. So so far, still the dominating school of thoughts is asset pricing. Um, so when people talk asset pricing, I mean, there's like like a bunch of papers online, but the easiest one I can explain is probably the CAPM model, or like the Markowitz. It's called, also known as the Markowitz bullet curve. Okay. It's this one here. It's this graph. So if you look at this graph, you can kind of get an understanding of the basic idea of asset pricing. You collect your data and you ignore the timestamp just for a sec. You ignore timestamp and then you collect data. You say, okay, what is the return and the standard deviation of that return um, for each stock? And then whatever that data is, you just plot it. And then if you plot this plot, then what's going to happen is you're actually able to draw this line called efficient frontier. There's a fancy mathematical model to teach you how to draw that line, and there's software to teach you how to draw that line. But basically, the idea is based on the assumption that you have a fixed amount of money and you can only distribute the money in certain stocks, assuming that you are aware that these stocks exist. The combination of the portfolio will never be able to go above this line. That's why it's called efficient frontier. And then assuming your risk-free rate is low, this is kind of like the treasury bond rate, it's very low. You can kind of draw a line that's tangent to this curve, and that dot there, it's going to be the best way to manage your portfolio, whatever the weights of that is. That actually doesn't really have anything to do with making predictions, right? So that's kind of like a caveat number one. And then when you write that out, it's actually going to be a linear regression model. And that linear regression model looks something like this. So this is just your market return minus risk-free, and then this is the return of whatever the equity is. So that's kind of how you think about it. And again, I say linear regression model. But the linear regression model here, it's still looking at historical data and doesn't really predict anything in the future. There's no t here, right? There's no time here. So even though these risk-free rate or return of the market is technically speaking tracked by time, the goal of this formula, it's not really to predict the next return in the future. Does that make sense? So I'm not saying that you shouldn't do that. I'm saying that the current school of thoughts, it's set up in a way that that assumption already failed. The goal, the assumption to allow you to make a good prediction already failed. So that's something there to worth notice. And then this is actually go on very big. The next step, which is called Fama-French three-factor model. Fama-French three-factor model. And then three-factor model looks something like this. So if you take a look at this formula, it's just a three-factor linear regression model. Like on the surface, there's like not really anything fancy about the formula. The creation of this formula obviously is very important. But again, there's no t here, right? There's no time here. These are just different way of partition the market so that you can kind of like rebalance your portfolio in a way that overall, hopefully it beats the market. So that's all that's happening here. There's no prediction here, right? So you can continue down this direction and keep adding factors. When I was at EQR, I work on this model like complete from scratch. But today I think Goldman Sachs, not even today, like I think 10 years ago, Goldman Sachs had a model that's 20 factors, and you can make money out of this factor. The more factor, excuse me, you can make money on this formula, and the more factor you're able to create, the more money you're able to make. And this is a real tested model in the industry that people make billions of dollars on it with real money, and it's highly scalable. And the reason it's scalable is because you can apply this on entire stock market. Um, so so that's something that's I'm not saying this is the only correct way. I'm just saying this is the way to think about how to use quant in stock market and to make money. Certainly, come on in. Certainly, it's possible to make money and be profitable in stock market using other methods. But this is one method that's already been proven that's working. Make sense? Any questions before I continue?
Do you feel that you're more optimizing for the weights and biases linked to predictions then?
Predictions of what?
So would you say that you're optimizing for the weights and biases
Yeah.
more than the prediction itself?
Correct. So that's a good question. So when you're optimizing for the variance. That's typically when people start. You want your portfolio to have the least variance. So variance is another way of saying smallest amount of risk. That's pretty much it. People don't optimize using returns because you want return to be as high as you can, right? There's no objective function to define how high the return should be, right? But you can define something to have like, let's say, zero risk, or let's say risk has to be 3% or 4% or whatever. So that's the way to think about it. All the way to here, nothing about prediction, right? Nothing about prediction until, God forbid, until this professor at, again, U Chicago. This is coming from U Chicago, is where I did my MBA. And then there's this professor called Reimagine Stock Returns or something. U Chicago. This one. Is this one? Yeah, this guy, Da-Chen Show. And then I actually took his class, by the way. I think he has an interesting story that doesn't work perfectly, but it so far is probably the only way to put AI in stock market and put prediction in stock market and works. So let me try to find something because I don't think you can download this, right? You might not be able to download this. Da-Chen Show. I just need to find a picture. It's difficult to find a picture. It's this guy. Oh, come on. That's a good one. I can probably talk about that. Yeah, okay. So that's enough. So this is how he did it. So he processed the stock chart into these kind of structures. So they're not candlestick, right? They're like kind of like its own style. And then he colored it black and white. So it's not color picture. So it's black and white. And then he basically limits a certain time frame, like a 5-day, 20-day, or whatever, 30 days, something like that. And then he used this as an input picture. And then what's gonna happen is you have to tag your label on this picture. Like for example, you can kind of, loosely speaking, you can kind of think about this as a day. So like each one of these bars a day, a day, a day, a day, a day. And then you track data for however many days this is, let's say 30 days. And then from here, you then look at the performance, let's say stock return of the next 5 day or next 10 days, something like that. Usually closer the better because then you can act on it. If it's too long, then everything's going up, then that kind of defeats the purpose. So usually this is kind of like, you can kind of call this like a 30-day chart in the past. And then you attach a label here that the next 5 day, the return of this stock price based on this chart is a whatever percent, 3%, 5%, or it could be -2%, -5%, something like that. And then you can then send this picture into convolutional neural network. So how it works is he has a picture here that basically re-explain the MNIST data set, but with the stock chart data. So the MNIST data set, it's a very similar design. And there's a reason that he does that, right? Because he knows that MNIST data set works. Like he knows that this works. So he's kind of like processing stock chart in a way that kind of look like this, or at least from data perspective, right? So MNIST is black and white, and then these are pixelated, and each pixel is like a number. It's grayscale. So he is doing the similar thing. He's saying, okay, these white bars is just kind of like a little grayscale change of value in your matrix. So if you look at the matrix form, it kind of just look like these guys. And then if you look at these guys, then you can actually create these filters that capture the pattern of what the pattern is in the stock market before the return is 5%, or before the return is -5%. So he's able to actually somehow do that. Okay, so now you have your picture, you have your label, you have a strategy. Strategy is how you process a picture. Now it's a kosher, right? You just, you stick the data into convolutional neural network and you just train it. Convolutional neural network says, okay, based on this picture, I think next 5 days is going to be returns 5%. Great, then you buy it. The next 5 days is -5%. Great, then you sell it. Something like that. And then he went ahead and did that. I don't know if that's a return here. Yeah, I have to find a picture that's like unblocked by the paywall. But the return is something like 53%. That's how low it is. 53%, it's kind of like borderline random guessing because a coin toss is 50%, right? I can toss a coin for 1,000 times, it's probably going to be 50%. And if you're telling me you have a model that's 53%, then you're just doing a little bit better than coin toss. Does that make sense? And then in doing so, he basically create a portfolio that runs this strategy. And then after you run that strategy, you then have to benchmark with an existing benchmark. And then that's what this thing comes in. That's what this equation comes in. So you have an existing benchmark, that's market. You have an existing benchmark, whatever that strategy is, and then whatever that strategy is. And then your portfolio, now the return needs to be here, right? So now you calculate the return of your own portfolio, whatever strategy you want, right? If you want to look at a stock chart and you want to have a convolutional neural network tell you what the return is, fine. That's your strategy. That's totally fine. Fair game. And then you can trade on that strategy, and then you calculate the return, and then you put your return here. It turned out that it doesn't really beat this benchmark by that much. There's maybe a little bit of signal, but not a whole lot of signal. And signal probably comes down to like a few basis points for per time stamp. If time stamp is monthly, probably per basis point per monthly. So it's a very very marginal return. And then now the question is the ROI, right? The return on investment. So you just told me you have a fancy AI algorithm that trains the neural network algorithm and then feeds in image data. And now you're telling me that you can make a few basis points per month or whatever. And then on top of that, you tell me you have to have expensive GPU to run this. And then if you scale this up, imagine how many GPU you need at a per minute level. If you want to trade this high frequency, let's say every minute you're putting like 100 orders, something like that. Then how much GPU do you need? And then what's the cost to do that? And then you work out that math, turn out it's probably not making you any money. The cost that you put in the GPU to run the inference of these images, like these guys, like these images, it's going to chew up the money that you made from beating the benchmark. Does that make sense? So point being, this is still a good paper from academic perspective, in the sense that he has a different way of looking at stock data, and then he did find a strategy that somehow beats the market on paper. Um, but certainly there's different caveats in the real world. But it kind of like opens the door of, okay, if you want to use neural network in trading, how like what's the framework to go about it? And how do you convince people that it truly works? And in his paper, he laid that out pretty much very detailed, like step by step. This is what you should think about if you want to convince people like how it works. Does that make sense? Any questions? Okay. Um, if you're interested, come talk to me after class. I'm personally interested in this. I think there's still more to do on this. It's just people haven't figured it out completely. Um, so yeah, if you're interested, just let me know, and then we can keep talking. So that's one thing about stock market. Next thing is the sports, because I know you had an idea, so I want to talk a little bit about that. Here's how I think about it. I mean, I might be butchering your idea, but this is how I think about it. Um, he had an idea last time that basically there's some sort of a web app or some sort of a platform that match the player and somehow predict the value of a player. It can be any sports, football, soccer, take your pick. And then it's a I think it should be a two-way market, but you can disagree. That's okay. I think one idea, when I look at the problem, I think one idea is you can turn this into a two-way market, and then you can let on one hand you can let people to put in the scores or put in the metrics of your performance, and then on the other hand you can have the scout to also hop on a platform, and then you just play the matching game, right? It's kind of like a Tinder for sports, if you think about it. So here's how I think about it. Whenever you have an idea, quickly turn into an app and quickly think about use AI and use app to think about it. So this is how I think about it. Let me move this here. This is a cloud code. So far nothing fancy yet. So this is what I said. I said I want you to build an app for me. It's a two-way market. One side of the app is to allow users such as school, PE teacher, or whatever to add candidates from school, football team, or whatever, according to different criteria. Now, me personally, I'm not a sports person. I don't really know what criterion is, but in your case, if you know what criterion is, then obviously like add a few more sentences in there to make it clear, right? On the other side, the app, you should allow different division of team coaches or their assistants to search out candidates they want to interview or screen for potential NFL teams, right? And then I want the app to provide a matching platform for both this people and this people. That's all I have to say, right? So from here, my job is done, and then I just wait a little bit. Now you just see what the app look like. So this is what the app look like. Let me zoom in a little bit. Sorry, that's big. So this is what the app look like. It kind of give me the idea of what my idea should look like, right? So that's kind of what this is. Um, and then whenever you guys have ideas, just quickly put it in a chat bar and then see what it builds for you, so that you can kind of like you're not starting from scratch, right? Like you're not starting from, oh, what's a table, what's a row, what's a column. Like you immediately have something that's tangible that you can work with. Now, of course, like you might not like this, but that's fine, right? That's how you get started. So I think I'm going to say a little bit of what's good and what's bad about this, and then I'll just land there. Because I haven't done much, right? I literally just talk to a chatbot for like 10 minutes. So I think one thing about this platform is that I personally like is it provides a match. And the way that you provide a match is you design a user interface in a way that it makes sense for two parties of people. The two party means uh, the talented football player or the talented soccer player that's still young, and the other side is the scouts, like whoever that's looking for these players, that's trying to buy them, like trying to sign them up to the team, right? So here you just pick and choose your role, and then it'll take you to a different UI. So that's just how you think about this design in the beginning. And then once you have the kind of like a baseline idea, okay, there's a button, you click on it, assuming your persona is this party. You click on it, assuming your persona is the other party. Okay, that's a baseline. You start from there. Now, what do you see? From the PE teacher, obviously, it should be like a list of students that in your school that you train, something like that. And then this is when you should think about what a criterion is. Now, I haven't entered any criterion, so I'm assuming the chatbot is like making things up. So if you have criterion, obviously this section need to be redefined, right? Um, and then this kind of give you a baseline to start. Okay, passing yards, touchdowns, completion rate, whatever this is. And then you should be able to like customize it, right? That's what this button is for, right? Edit profile or something like that. And then you can view an analytics. I don't know what this does exactly. Probably does nothing because this is just a front end app. It's meant to just display your idea. Um, and then you can continue so on and so forth. Those are the students. Um, my player, and these are your player. You can add player if you want to. But the moment that you start from here, now you're thinking about, okay, what the database need to look like, and if the database need to look like this, how big the database need to be, and where am I going to store that, right? So now it gets the ball rolling and it helps you think about certain things when you're designing an app like this. So that's one side, right? Now you can talk about the other side, which is NFL Scout. Um, oops. Yeah, Scout. So Scout, you can have dashboard, probably see same amount of students, same amount of data, just as a default setup. But for future reference, I'm assuming there's some sort of like because if it's your company that you're doing this, then I'm assuming there's some sort of like a paywall around it. Like they might have to pay a fee to see some of these stats, right? Like, because you build this website and some of these numbers might come from AI software. Like for example, these stars here or whatever, that might come from AI software. And then if you own the AI software, you own the code, then obviously it shouldn't be free. So those are things that you can now start thinking about what that product look like. And then you can say search player. Now this makes it very interesting. You can do a very generic search like this. This just means like you go with different rows or whatever. So it's no different than in an Excel table you filter. Right? That's no different than that. But what if you can actually make this into a chatbot and then you can just talk to it. You can say, hey, I want someone as a wide receiver, and then chatbot will bring up the data for you, right? Now we're talking about the retrieval augmented generation, and that will make things very interesting. So now your product has AI in it, has chatbot in it, has RAG algorithm in it, and that's how you get the ball rolling, right? So now that's something that investors will want to pay for. And then you have grades, you have states or whatever. These are just the criteria that we talked about, right? Again, you may or may not like this criteria, totally fine. You can very well define your own criteria, right? And then you can engineer criteria in your chatbot. And then the next session, we're going to talk about what that means, because we're going to show you guys a little bit about that. And then you can bring up the data and then you can present this table. And then you can redesign this UI in a chatbot manner so that user can talk to it and then you'll bring the data back up. A table is perfectly fine. I think it gets things started. But you want to be fancy about it. And then if a user doesn't know, like imagine you update this website 50 times and then you have like 100 of these criterions here. That might very well be the case because that means your algorithm is now very proprietary and then it takes a lot of cost for you to train an algorithm. You should obviously own the algorithm. But you can make the argument saying, okay, my neural network model has like 100 features. You're not going to have a user click button 100 times, right? So in that scenario, that's where chatbot comes in. So chatbot replaces that cost, the overhead cost of the search in the database. That's all. That's the most frequent use case in today's Gen AI world is they use large language model as a way of searching database. Make sense? So that's a search. That's a search page, and then whatever the AI matches is, I'm assuming there's some sort of like a feature that the scouts enter in. This is the player they want to choose, and then based on this criteria, the AI algorithms give you like a list of players. If you're able to build this like a full stack app, like to up to this level and even more, and then you're able to like imagine the search player has this table, and then somewhere down here there's like a chatbot or like a chatbot here. You can talk to it, and then it updates this UI automatically. Like if you can able to get to that level, like trust me, someone will pay for that. And that's a very viable product if you can get to that level. Does that make sense? Any questions? Okay, good. We're coming up at the clock. Um, yeah. So point of this is, I think it's a great idea. I think it can turn into something highly tangible, and I'm showing you guys this exercise. Just hopefully you guys use AI to quickly envision what the idea is, and then just build upon that. And then there are all these, and this comes with a code, right? Like you can just take the code and reinvent the wheel. Like you don't have to code from scratch. Um, so yeah, I'll leave it there, and then let's take a 15-minute break, and then let's come back. It's about 7, so let's just come back 7:15. Okay, yeah, let's take a break. Okay, so can everyone see this? You want me to zoom in a little bit? Is it good? Or is that good? Okay, okay. Yeah, just let me know if you can see it. Okay, so let's talk about this a little bit. It looks oh it looks it looks easier than it looks harder than it actually is. So I want to explain this a little bit, at least on a high level. So when people are building their own apps, at least you're a little bit of aware of, okay, if you're going to handle multimodal model, exactly what that means. So as a recap, previously, when we're loading a language model from scratch, you have to load in two things, right? You have to load in the tokenizer, you have to load in the model. So there are two things you have to load into your computer, right? Whatever computer you're using. It could be CPU, it could be GPU. CPU obviously slower, GPU is faster. But theoretically, both should work. It's just a matter of speed. Now, same goes with VQA. The only thing different is when you are handling VQA, you have to load in like three things. Um, so install Gradio, install transformers, and then let me show you the code a little bit. So that's pretty much it. That's how big the code is. It's not a not horribly long code. And that's how I like it. Okay, so what's happening here? First three lines, you just import all the packages. That's pretty straightforward. Here, um, when you're loading the model from Hugging Face, uh, first and foremost, it depends on what the provider of the model does, right? Uh, Salesforce is a company, they have their own AI team. They're gonna do things in their own way. Meta's going to do things their own way. Google's going to do things their own way, right? Depend on what each company is doing. Also, the transformer package is also open source, right? Hugging Face open source, Transformers open source. So likely they're going to have their own function. Does that make sense? And sometimes when you go from one version to another version, there's also different function. Okay, so what I'm trying to say is it's probably not going to work if you just copy the same code and then you just change its name. It's probably not going to work out well. And even if you magically get it to run, it's probably not going to be accurate, and it's just gonna start saying nonsense. So that's one thing I want you guys to be aware of. Watch out for the provider. Watch out for the configuration of however they did their model. Right. So that's the one thing. Okay. So processor model. Once you load those two things, here we're dealing with a VQA, right? VQA stands for vision question answer. So not only are you talking to it, you're also sending a picture, right? So the framework here is inference and inference on a model that already exists. So we're not fine-tuning this model right here. We're just pulling the model's weight and we're just run data through inference once. So that's what's happening here. So let's talk about this function a little bit. This function has two inputs, image and question, right? For obvious reason, right? You want to talk to it, there's a picture, therefore the input argument is image and question. So that should make sense. Handling the error, so that's there. Here, you're loading three things, right? What are they? Inputs. Inputs here are image and question. So whatever this image is, whatever the question is, just throw that in there. That's the two arguments. And then the output is actually the token generated from the model, and it's literally trying to guess the next token. And it's trying to guess the next token based on the image and based on the question. So that's what it's doing. And then on a high level, I think I have a picture here. Let's see. So this paper, oops, let me put it here. So this paper is essentially what our model is. It's called BLIP, Bootstrapping Language Image Pre-training for Unified Vision Language Understanding and Generation. And you click in their paper. The idea is very simple, right? You have a picture, and then you send it in here, and then you're just trying to caption it. If it works, then great. What they're saying here is they use this technique, and therefore it works. The original technique doesn't work. So that's what that picture is saying. This is the architecture. So to explain you guys this architecture, I actually need to explain to you guys VIT, Vision Transformer. And Vision Transformer is essentially the backbone of this architecture, right? So Vision Transformer has two things: has vision and has transformers. That's kind of it. And so let me take you to that detour, and you kind of have to understand that because otherwise you won't be able to understand this. There's a picture here. That's it. This is a picture. Okay. So how does VIT work? VIT stands for Vision Transformer. Two concepts. One is picture. Second one is transformer. So transformer is the model that powers ChatGPT. Literally, it's in its name. GPT stands for Generative Pre-trained Transformer. So that's what transformer is. The special thing here is the image and how they process it. So how they did it is they take a picture and then they cut it in different patches. And then these patches, hopefully, and obviously knock on wood, hopefully captures the pattern of the picture. So these patch actually behaves in a very similar way as the features generated from the convolutional layer in a conventional convolutional neural network. The only thing is these patches are much larger. These patches are like if this picture is 64 by 64 and you cut it into 9 patches, then it's like 64 divided by 1, 2, 3, so 3 by 3. So 64 divided by 3. So each patch is like 20 something pixels. Whereas the original CNN, each small convolutional object is like 2 by 2, 3 by 3. So we're talking about a very different scale, right? The original one is like 2 by 2, 3 by 3 pixels. This guy here, each patch is like 20 by 20 pixels. So scale is going to be very different. Now, what are you going to do after you cut the picture into small patches is you basically lay them out. And then in this case, this is actually a crucial argument here. It's this linearity assumption here, which actually a lot of people don't like it, which is very interesting because the people who don't like it, they're saying, okay, why do you make a linear assumption? It's not linear, right? It's not like this building has to be happening before this cone here, and then happening before this cone here, happening before this building, right? There's no like once you break that apart into their own different thing, and then you assume that's linear across all these different patches, then the geographic, the spatial relationship no longer exists, right? So people who argue or people who criticize this model, that's their argument, and it's actually a fair argument. It does destroy the geospatial structure. But how are they able to get away with that is even though they destroy the spatial structure, they're actually able to reconstruct the picture back because of the transformer layer. And that's why they're able to get away with that, because it's precisely because the power of the transformer encoder. So a transformer encoder actually does not care if this cone is behind this cone and it's behind that part of the building. It actually doesn't care about any of that because the transformer layer actually was able to tell, okay, the embedding of this picture, excuse me, the probability of the embedding of that patch of picture, not the patch of picture, the embedding of the patch of picture actually is like say 60% if you want to go from this patch to this patch. And then since transformer give you a transition probability in the end, it actually knows the probability of this patch here to all the other patches.
Transformer already has a positional encoding, right? Why don't
Exactly.
encode it?
That's precisely what they're doing. So that positional encoding learned the pattern of one patch to every single other patch for all the patches inside. So they're actually able to get away with, technically speaking, there's a little flaw there. They're actually able to get away with that. So it's a very neat design. It basically what this look like is, it kind of looked like I'm walking into a wall and I'm gonna hurt myself, but somehow like I'm able to get away from that blocker. So that's what this looked like. And it's a very elegant structure that's able to pull this off and train the data and show that the performance of this is actually pretty accurate. Um, so long story to explain, you can break the picture up in different patches, and you can pull it off. That's kind of a long answer to explain that. So now once we understood this, right? Once we understood this, we can then on top of sending in a picture, you just send in a sentence, right? And then you just learn whatever it is you want to learn. You tag another sentence down here, and then that's how you train a VQA. So that's how VQA get trained, and then the structure of that kind of look like this. Picture, you break the picture into patches, send that into attention layer, and then you do the same thing with sentence. And then you just bring everything back together, and then you make a prediction. So that's that. And then the same time, this you can actually do whatever you want. You can send this whole sentence into encoding. You can break them up into different tokens and then send into encoding. You can have this 2, 3 times or 3, 4 times, however you want. That actually turn out doesn't matter, because with enough GPU, you can always build more attention layer inside or transformer layer inside, and you can build as many as you want. That's fine. That's like a choice of parameters. Excuse me, a choice of hyperparameters. And then in the end, you treat it as a language model, and then you just make a prediction. So that's a diagram. Now let me show you. Now let's go back to the code. So that's a long explanation of what goes inside that model. So that's what that model is doing. It's basically a bunch of numbers, a bunch of weights that explained what I just showed you here. Make sense? Okay. So you have your inputs, you have your outputs, and then whatever this output is at this moment, line 14, at this moment, this output is still the tokens, right? It's not words, right? So in the end, you convert the output into the answer, and then you return the answer. Make sense? Any questions? So okay, so that's the function, and then so you can kind of call that I think previous class we call this the backend, right? It's a function that does the magic that on the user interface probably user don't see that. Great. So that's the backend. Now this is the front end. So front end is also pretty straightforward. Fn means a function, and function is whatever you define here. VQA answer, then you stick VQA answer in there. And then input is image and text. So Gradio image, Gradio text, that's there. And then whatever label you want to add, that's perfectly fine. And then in the end, you return another text, and that's it. So this chunk of code, you can kind of consider that front end. So you have code for backend, you have code for front end, and then you just launch the app. Make sense? Any questions? Okay, so it should be relatively straightforward and kind of by design it's straightforward. Now I'm gonna show you guys what that look like. I have one loaded here. I can probably take a picture. I'll just take a picture using my phone because it's connected. Okay, so what's in the image? Okay, let's see what it says. Keyboard. Okay, great, it worked. This current model is loaded as it's a blip VQA cap lift large. Excuse me, a cap field large, and then the cap field is just the design in the paper. It's I think they said a little bit here. It's this thing, caption filter. So it come from this paper. And then you can take the code from GitHub and then do whatever you want to do, and you can fine tune your own thing. I actually have a notebook here that allows you to fine tune the model from Google called Palgamma. It kind of looks like this. I'll show you the complexity of this. Um, so you're gonna have to have some sort of base model, and then you need your data set. Excuse me, that's not model, that's a data set. And then you need to have some sort of base model, which you can take Paragamma. And here it's a 3 billion because I think if you go larger than that, this GPU will probably crash. So that's there. And then check your token, process it. You can use this as a helper function. And then after that, you should be good to go. Where's the code for training? This is the code for training, and that's pretty much all you need. And then this is also kosher if you want to use deep speed package, because deep speed package allows you to distribute your training to multiple GPUs if you want to use that. And the training argument is come from transformer, and you can just plug in like a JSON file for deep speed package if you want to do that. And you can try to train it, and then you can push onto Hugging Face, things like that. I'm gonna add a link in the video after this is recorded and uploaded, and so everyone has access to this. It's pretty fun to go to this, and you can kind of like take random pictures and just adding sentence yourself. Um, which means you're gonna have to somewhat create your own data set, right? There's actually a simple way to create your data set, which is you run through inference using Anthropic, or you can do that with OpenAI as well. But I actually have code here to do that for Anthropic. So this is how you do it. So you take a link, whatever link it is. It can be any picture that you took, right? I'll just show you what the picture look like. So like an animal, an ant. Um, Same goes with this one. Let's see, it's probably a bee. Oh, does that look like a bee? It looks like a fly to me. I don't know. It says bee here. Whatever, like it's an animal. And then you have your Claude API key in here. You can send in an image, and then it will describe something back. This is a detail of an ant showing its distinctive body structure, so on and so forth. So this way you at least get the image picture, excuse me, the image description pair, right? And then now all you gotta do is tag a question to it. And then the question can simply be what's in the picture. And then the answer is the sentence here. So now you have your image, question, answer pair. Make sense? And then you can fine tune your own VQA model. Any questions?
So you're generating it from Claude and then
Yeah, yeah. Cool. So I'll leave it here, and then for people to play around if they want to play around. It could be a fun project, but obviously depending on what data you have. Um, I think in the industry, animal picture probably not a whole lot of impact unless your job is to work with animals. But if you're like looking at finance, it could very well be stock chart. If you're working in like healthcare, chances are you're probably working with a lot of documentation. Then it could very well be a picture of a documentation. So depending on the question and the answer in your training data, you can actually customize the VQA model to pretty much carry on a particular task for you, just based on what document you have. And you actually don't need a whole lot. People get away with like 20 pictures, and you can easily just take your phone, take 20 pictures. Like I can do that in like a minute. And then that's pretty much the framework for handling VQA. You have a question? Yeah.
that just give you sort of insight. Um, let's say you're working in the animal industry, and then you want to tell the difference between certain animals like snakes. That when you take a picture, it should be able to tell you that this snake is venomous. Don't approach.
Yeah.
Is there a way you could tweak it and then do something like that?
Yeah, you can. If you have training data that's image of a snake that you know it's venomous, and then you tag the question and answer to actually say that, you can train a neural network model to memorize that. Yeah, that's possible. Yeah, but very possible. And I don't think you need a whole lot of data set. I think because the base model is insanely powerful. Like some of these off-the-shelf base model, it's extremely powerful. Like you don't need a whole lot to do what you do at a high accuracy. because animal pictures already out there. Like these models know it's a snake, right? Like you're not training from scratch. Um, they already know it's a snake. You can tell it's a venomous snake, right? Um, so yeah, that's totally possible. Yeah. The difficult part is words. The sentence, the words inside of a picture, that's the difficult part. So you want to take a different base model, but the training strategy is pretty much the same. Okay, so I can reduce that. And then now, with the remaining time, let me show you the RAG algorithm. So it's a different way of the RAG algorithm and VQA kind of, well, depending on what the vision is. So if it's an animal, that kind of like it's a different story. But if your VQA model, the picture is some sort of a document, then if I could like essentially what you're looking for is you're kind of like talking to a chatbot to see what's in the picture, and hopefully the chatbot can read the sentences in the picture, which is a document. So the alternative to that, it's this algorithm called retrieval augmented generation. Anyone heard of it? Okay, it should be pretty common right now. So RAG, retrieval augmented generation, basically means instead of just talking to a chatbot, you have a small search algorithm to search for the most similar content, and then you use the content to enhance and augment what the chatbot response is. So that's essentially RAG. And then there are so many frameworks out there. The framework I'm going to use today is called Milvus. Um, the reason I use Milvus, it's because it's easier to scale up and push in production. That's the only reason. Any other package out there, totally fine. It will do the same job, but you're gonna have to build your own package. Milvus is package ready, it's container ready. So that's the only difference. So I can walk you through this really fast. Um, so you install it, and you install that. And then it only requires a couple of simple steps to set up uh, uh, the collection. And once you have a collection, you can then start sticking data into that collection, and then you can start use it. It already has a model behind the scene. It's a Hugging Face model to basically look for the most similar content. So the point of the demo is I want to at least show you guys the context. So if you do decide to build some sort of search engine that's chatbot based, it will be some sort of RAG algorithm to begin with. Um, so that's installed. I'm gonna say build a client. Oh, what's happening? Did I not run? Let me restart. Let me try again. Oh, come on. I tested this earlier, it worked, but somehow it's not working. Let's see if we can get past that. And then this is install. Let me try this again. Oh, come on. Let's see. I have to install this. So that's annoying. They might have updated the package. I tried this yesterday and then it didn't bug me with that. Interesting. They could update the package. Let's see if this works. Okay. Okay, it worked. Okay. So I just have to install that package. So this give you the client. It's the same framework as if you're loading like a OpenAI client or whatever, Hugging Face client. It's the same framework. You can check if it has collection or not using this code. Just make sure that this name is not already predefined because the name does have to be unique, right? Because it's a database. And then the thing here says 768. It's dependent on the model behind the scene. In this case, I think they use BERT or something like that, or mini BERT. And then the length of the vector is 768. So that's just pretty fine. So now you can kind of create your own embedding and then find a couple of documents. So these documents are just fake documents, right? It's just an array of 3 sentences. Nothing special here. It's just made up on the spot to demonstrate a point. In reality, this string can pretty much be whatever you want. It can be a table, it can be some sort of JSON file, it can be pretty much whatever you want inside. It will run through the similarity search in the same manner. But this is how you define the documents. And then once you have this documents, it's array of string, right? You send that into the embedding function, and then it will give you the vectors, and then you can check the dimension of the vectors, and then hopefully it says 768. If it doesn't, then something's wrong. So you run through that, you wait a little bit, it should say 768, and then what that effectively means is it's running the vector through the this for loop in here, which is here, that check the length of each vector, and then the length of each vector should be the same, and they should all be 768. So just like what it's saying here. So that makes perfect sense to how the collection is being defined. And then here there's 3 entities, and that makes sense because here we have 3 sentences. So this kind of give you a quick way of processing your data to make it ready to plug into that collection. So now the next step is you want to then insert it into the collection, and you count it real fast. There are like 3 items in there, and that makes perfect sense because you have 3 documents in there. Once that's done, you can then run your semantic search. Semantic search works like this. You need to say something, right? You need to say something, and then how it works is you will take what you said, use the same model to process that into vectors, and then it calculates a similarity score of that vector with the vectors of the documents that currently exist in the database. If it doesn't exist, then obviously you can't find it. But if it exists, then hopefully it will give you a similarity score that's based on the distance of those vectors. The higher distance, the worse you are. I'm going to explain that part in just a sec. But let's run through this code. It will give you this kind of result. And then what this result says is you have like ID of the document, and you have a distance. Here says 0.58. And then if you scroll to the right, you have another document here, distance is 0.51. So here's the caveat. The distance, actually, the larger the worse it gets. You want the distance to be small. So 0.58 is larger than 0.51. Then that's the content that is not very similar to this question that you're asking right here. So who's Alan Turing? Then this sentence makes more sense in terms of what the user question is asking. Does that make sense? So that's kind of like a simple RAG algorithm to help you understand how it works. Now, here's the caveat. The only math here that's worth understanding is probably this distance score. And this distance score is actually just a cosine similarity. So how it works is it's processing the, let me make sure I can, let me open, hang on one sec. So it goes something like this. I'm gonna add notes here. What does it mean exactly? You know what? Let me add it up here. So semantic search. It's relying on this formula called a cosine similarity. So how it works is this. So this is cosine similarity, or you can probably just call cosine scores, probably easier. Okay, so how it works is assume or say suppose we have 2 vectors, and then you can basically call it v1 and v2, something like that. The cosine similarity or cosine score is defined as something like this. So you can call it cosine v1, v2, v2, and then here it's a fraction. The top of the fraction is the dot product of the vectors, and these are the vectors of 2 sentences. So you can kind of think about this as dot product. So I'm going to use parentheses. Actually, let me use parentheses. Fine. So v1 dot v2. I forgot a sub. V sub 1 and v sub 2. And then the bottom is the multiplication of the norm. So norm, you can kind of use this kind of symbol, v1 times v2, something like that. Oops, I forgot close the parenthesis, like that. Okay, so the quick exercise here, and this math is worth doing. So assume that your v1 is something like 0, 1. Okay, and then assume that v2 is 0, 2, something like that. Then the cosine score is so you calculate the dot product, which is this 0 times this 0 plus this 1 times this 2. Does that make sense? So it's kind of like position wise, it has to match up what dimension that number is in that vector. So it's 0. Let me do this in 2 steps. So top of fraction is 0 times 0 plus 1 times 2, which is just 2. And then bottom of fraction, this is the norm. So you have to calculate the norm of v1 and norm of v2. So norm is this guy here, v1. And this is going to be like the square root of, it's a square root of 0 squared plus 1 squared. And 0 squared plus 1 squared is 1, square root of 1 is 1, right? So norm of v1 is 1. And then norm of v2, same with this one. So 0 squared, 0, 2 squared is 4. And then take a square root, so back to 2. So now this is 2, and then just 1 times 2. So final result of bottom is 2. And then the final result of the fraction is going to be 2 by 2. Make sense? So 2 by 2, that's just 1. And that's essentially how the math works. So any questions? Good. Okay. So what this number measures, geometrically speaking, it's essentially how wide the angle is of 2 vectors. And the vectors, you can kind of think about it as these guys here, like 0, 1 as a vector, 0, 2, that's also a vector. And 0, 1 and 0, 2 in the real world are the numbers, the vectors come out of the embedding layer. And the embedding layer is completely dependent on how you train the language model. Okay, so that's that. Any questions about this? Okay, now that's kind of like the boring part. The fun part is this. Anyone take a wild guess at what point can this go wrong? In what scenario is the math lying? And there's more than one answer. Just think about the context a little bit. So let me rephrase the question. So everyone's on the same page. So we did the math, right? We did the math. We say, okay, here's a word, send them to language model, it'll give you 2 vectors. Great. And then you want to find a closer sentence, so you calculate the cosine similarity. Great. That's the math. Awesome. We did the math. Okay, fine. When does this go wrong? Like there's something in the document that if something happened, this doesn't work anymore. Can anyone take a guess? You can think about it a little bit. There's more than one answer, by the way. So think about what that scenario is. Yes.
There is a character that is not present in the document, then you might go wrong because you don't have a vector associated with that.
Okay, so I like where you're going with this, but can you repeat again, just so everyone can
If there
hear?
is a word that does not appear in,
If it's a word that
yeah, then it cannot associate uh, it to the document itself.
okay, so you want to be a little bit careful. When you say you said there's a word that
Doesn't exist in.
doesn't exist in the document, but do you mean word or do you mean the word going through the
Yeah.
embedding layer?
When you embed, I mean, encode the word and then the vector does not associate with the document.
When you have a word that doesn't go through, okay, that's one thing. And do you yes, first of all, you're correct. That is one scenario. But do you know why that give you a score that's wrong?
Because the way it is associating values to when you're creating the vector database, will associate values to specific topics and specific contexts as well. As it is out of context, that
Yeah, you're kind of like almost there. So let me rephrase your answer a little bit. That's actually correct answer. So if there's a word that doesn't that the training data of the language model this embedding layer is created from hasn't seen it before. That's what you're trying to say, right? The word doesn't exist. So the model that uses in excuse me, the embedding layer that generates the vector come from a large language model that's trained on the training data that word never existed. That's when the problem happens. So when that is the case, when that is a scenario, what we'll do is because the model hasn't seen that word before, so it will probably automatically assign to like this other tag, whatever that other tag is. So in the literature, there's this concept called a data desert, right? So that's effectively what that is. So you said something, a word. What if it's a new word? What if Gen Z made up a new word saying like vibe check is a word that doesn't exist in Oxford Dictionary, right? So something like that can probably be considered as because it's cultural, right? It's a new thing that people just made up on the spot, and the data hasn't seen it before. And when that happens, it will either find a similar content, hopefully, knock on wood, right? If it doesn't, that goes right into data desert. And data desert, it's I typically don't like that. I don't like you being in a data desert. It's actually a very dangerous thing in terms of your own interaction with other people. Same thing goes with here. If you have a word that's in the data desert, then you kind of screw because that word can never be processed by any model. That's a problem. Now that being said, data desert itself is technically speaking a cluster in the vector universe, right? If you think about it that way. So what I mean by that is this. Let me find the vector embedding uh, picture, just so everyone knows what I'm talking about. Uh, it's kind of like this. Yeah, this is probably the easiest picture I can pull up. Let me put it here. So you take each word, send them through the language model. Language model give you a vector, and then you plot it, right? Once you plot it, it looks something like this. Each of these circle, you can kind of think about it as one word. And then when you plot it, you realize you look at the word on the data, and it turns out that the similar context of the meaning of semantic meaning actually allows you to plot that dot, that circle, in a closer range. So animals are probably going to be all in one spot, and then the fruits are going to be on another spot. Same goes with pretty much anything else in the world, right? And it goes all the way to like the political world. If you're left leaning or if you're right leaning, they're actually able to find where you are on that cluster. Same goes with LinkedIn, TikTok, Instagram, pretty much all that stuff in your phone, right? Because it's constantly collecting data and it knows exactly where you are in this picture. If there's a like imagine the entire internet is just a three-dimensional dots, like a bunch of dots, and these are just data points. And then you and your behavior at a certain point in time, it's represented as one of these dots in the entire universe of data, in the data universe on the website, on the entire internet. So how it works is um, whenever you exert a certain behavior, a word, a document, you text somebody, you took a picture, all that stuff counts. These are all data points collected by your phone. All that data goes into something like this in a data universe, and it gets stored as one of these data, and that comes back to enhance how close you are to the centroid comparing to that cluster. And once it knows that you are in that cluster or center of a cluster, it will always assign you content that's similar, that comes out of that same cluster. Data desert, it's its own cluster. It's probably some cluster down here that's just a bunch of words that no one knows what that is. So that's effectively what data desert mean. And then it's dangerous with a simple meaning because the cosine similarity calculated using that vector no longer represents what that vector is in the real world. So that's what that means. Any questions? Okay, cool. Let me see. I think we're right on time. One last thing I'll say about this is, it will be better if so a couple of things you can do here. So one interesting project, just trying to give you guys some idea. One interesting project is you can take like a book or like a notes of something. I mean, it could be a lecture notes if the other professor allows. And then you just scrape the PDF, scrape your notes, and then create these documents. And then you can basically stick all that documents into one of these collections, and then you have your own database for that book. And then you can then just build some sort of chatbot based on the query. Where's the query? Something like this. You can engineer this in a Gradio app, and then this part of the sentence can be the input of the app, and then this stuff here can be the output. And then you can kind of display a table of what what is the most similar to what the user is asking. Does that make sense? Same goes with your project, right? If the database is like these content here, let's say they are not books or whatever. Let's say they are players, stats, numbers, the heights, the weights, how fast they run, whatever, like all that stuff, the criteria that you thought of, they can go in here, and then they can be searched based on whatever question that you type in, and then it will give you back this table, and then you just bring that back on the user interface, and effectively you'll be able to build your own search engine given the data that you have in your hand. Does that make sense? Cool. So hopefully this gives you like a little framework of how to do that and pull that off. And then Milvus is one thing. Obviously, there are more than one thing. Like the other famous one is called Chroma. Anyone heard of Chroma? ChromaDB. Yeah, yeah. So this one here. So I think there are a million tutorials online. You can run it. It's very simple. It's pretty much the same idea. Install package, same thing, right? There's a Chroma client. Whatever documents in there, you just add it to the client, and then that's pretty much it. And you just talk to it, and it will run the query for you. And basically, all these packages are the exact same algorithm. It's just the similarity score that we talked about. All it's doing is it's running this math, it's running this equation of your query and the existing query of whatever's being added to that database. Make sense? Any questions? Okay, good. Let's stop here. That's pretty much it. Let's stop here. And then, yeah, hopefully this will give you some idea of your project. Best of luck. And then, yeah, I'll see you guys next Friday. Yeah.